what do you call x on the calculator for a power series? Do you want to graph this? See, that's the problem. If you don't know the interval, you don't know what x can be. So in GeoGebra, what I did here, just to get a sense of this thing, the first curve I graphed here is this one right here, and that's if n equals 10. And then this one here is n equals 11, 12, 13, 14, 15, and the last one here is 16. See how it's extending itself each time? So the more terms, so looking at this, would you guess the radius of convergence is bigger than 8? Because they start to separate after 8. Now that's only 10 terms. What if I went, and that's the 16th, what if I went out 100 terms? See if GeoGebra can handle 100. Isn't it pretty cool? Ooh, look at 100 terms goes way out here. So based on the 100th, oops, and GeoGebra freaked out. Does it look like the interval of convergence might be greater than 8, the radius, I mean? Because look at it, starts to settle down. This is, so remember, this is the, let's see, 10th, 11th, 12th, 13th, 14th, 15th, 16th partial sum is here. This is the 100th partial sum out here. And GeoGebra ceased to be able to function. It just locked up. So what might be guess about the radius here? And maybe it's infinite. That happens sometimes when there's factorials involved. Okay, so let's explore with the ratio test. You got it? So we have to clean up. Oops, I guess I don't need the negative because I have absolute value, right? So I think I'm just going to ditch that up front. When you put the n plus 1 in, did you do it like that? Yeah. Okay, you got to have parentheses when you substitute n plus 1 for n. Is it okay if we say 2n plus 2? You could just call it 2n plus 2. You can just jump right to that if you wish. Okay, so there's a sub n plus 1. I'm going to flip a sub n over here. And then I'm going to clean this mess up. All right, so we do need to be careful with factorials, but I think the factorials are pretty straightforward here. What does n factorial squared mean? It means n factorial times n factorial. So that means down here I must have n plus 1 factorial times n plus 1 factorial. And we know those cancel nice, right? So other stuff, let's see. So here's what I think I'm left with. In the denominators, I'm going to get an n plus 1 times an n plus 1. Okay? Otherwise, there's nothing left of the n factorials in the top. As far as, so these guys are dealt with. As far as the 2's go, I believe I have a 2 squared left in the bottom. And I believe I have an x squared left in the top. Okay. So let's see, do I still need absolute values? Notice I ditched them. No, because you took out the negative 1. I took out the negative, well, usually with x you do need them, but the absolute value of x squared is still x squared. So that's okay. So turns out I don't need the absolute value at this point. But you always need to be very careful with that. All right, so now I need to take the limit of that blue stuff as n gets big. What happens as n gets big? The numerator's fixed, the denominator gets bigger. Yeah, so this thing goes to 0. Yeah. Okay, so by the ratio test, our limit as n increased of the absolute value of a sub n plus 1 over a sub n went to 0. Ratio test says that that should be less than 1. Since x isn't present, that means it's true for all x values. Okay. True for all x, which implies r is infinite. Now this is one of the one of the few places we'll actually write infinity equals something, because infinity is not a number, right? Except in JavaScript. which I just learned that. Did I tell you guys that last week? JavaScript treats infinity like a number. Just kind of blows my mind. Yeah, physics teachers treat it like a number. So what's the difference? JavaScript, physics teachers? Okay, it can be sometimes, yeah. All right. So what's the interval of convergence then? Yeah, it's all x values, right? Yeah, so the interval, do we have any endpoints to check? Oof, that's why I love the radius being infinity, because you don't have to worry about the endpoints, because that's usually, you know, twice as much work added on. So the interval, negative infinity to infinity. All right, that was pretty cool. By the way, this is called what's called a first order Bessel function, and it comes up in studying waves. Waves, yes, oscillating motion. In particular, this one, notice that, oops, what's that? Okay, notice that this wave is the amplitude is dropping. Can you see that? The wave height is dropping as I go on. So this is what's called a damped oscillator. If GeoGebra can't seem to handle looking out farther, it's dying. Maybe Wolfram Alpha can probably show me more. Yeah, Wolfram Alpha shows a better view here. So it's going to be dropping over time. And eventually, what we'd see if we took the limit of the function, not the ratio test is totally different, but the limit of the function, looking at the amplitude, we see that the amplitude is going to go to 0 over time. But it's going to take forever to do so. Okay. So this is a damped oscillator here. So it's kind of like, you know, a spring with friction. Eventually, it's just going to stop bobbing up and down. Okay. So so if you get a course after this, people usually take as differential equations. And so this is an example of a solution to a differential equation. Now, the cool thing about this is a very important function in physics, but the formula for it is that series. That's it. It's not like a sine. It's not a cosine. It's this series. And this function is so special, it's given the name J sub 0. Yeah. I don't know where the J came from, but a guy named, these are attributed to a guy named Bessel. I think he was around in the late 1800s, if I remember right. Let's look that up. Yeah, so for hundreds of years, people were trying to solve these wave equations, and it wasn't, Newton knew about them, but he hadn't solved them. He knew they existed. He had an idea, as we believe. It wasn't until after Newton's time that people finally got a grasp on them a little bit. And it wasn't, even in this century, it's still kind of, there's a lot of things we still don't know about some of the equations that lead to these particular functions. Okay, so before we were talking about, why the hell do we need power series? Well, because they open up a whole new class of functions that we couldn't talk about otherwise. Without power series, the Bessel function would not exist. Yes, ma'am. Well, if we wanted to study any kind of system where things have a damped oscillation, so pretty much every system, I mean, there's no such thing as a perpetual motion machine, right? So like for that clock to keep spinning, I got to use energy to make it happen. Without that additional energy all the time, not yet at least, right? No perpetual motion yet, things dampen over time. And so the Bessel function is one example of how things can dampen over time, how they can run out of energy. Does that help? Yeah, and it affects a lot of things. It affects, like, if you hit a metal beam or anything, it's going to vibrate, but then it's going to stop, right? That's the damped oscillation. They're everywhere. Sounds fade, right? Damped oscillation. Right? So just about everything around us is some kind of damped oscillation. Isn't it awesome? Yeah. Everything is waves, it turns out. At least that's one look at them, one view of them. Why do they do that? I don't know. Okay, so away from philosophy for a minute and back to math. Okay, I got another series for you. So we developed a power series for e to the x by taking repeated derivatives of it. Okay, and we discovered that its series was the sum, as n goes from 0 to infinity, of x to the n over n factorial. Right? Which, if we write it out, that's 1 plus x over 1 plus x squared over 2 plus x cubed over 6. What's next? 24. X to the 4th over 24. Blah, blah, blah. The nth term being x to the n over n factorial. If I decided to stop at the fourth term and ignored that this thing keeps going, so now I just have, let's write it in red, the sum as n goes from 0 to 4 instead of infinity. Okay? It's not an infinite series anymore, x to the n over n factorial. Okay? In this case, since this one came from the derivatives of e, it is called a fourth degree Taylor polynomial. Like, did you ever wonder, like, where the heck does e to the x come from? Like, how do we calculate points on the curve for e to the x? Well, to do so, we need to know e, but there's a problem with e. What's the problem with e? Its decimal goes on forever, so we really can't write it down in its entirety as a decimal. The calculator just approximates it. Okay, maybe it has 15 places. That's a pretty good approximation. But at some point, it's not going to be a good approximation for certain values. Okay? So this is one way we can approximate some of those values. So you just decide what your error is going to be. Then we plug in a number, and we use this to figure out how many terms we need to make it a reasonable approximation. So just for fun, let's graph that on the calculator. Do you have a calculator with you? Jeff, come on, man.
Looks like an exponential function. That's funny. It's kind of weird.
So we could do a sum sequence in the y equals menu. That would work. Right? Just like you do anywhere else. So you're just going to go to, where is it, under list? Oops. And then ops, a second stat to get list, right? And then under, let's see, math is sum, number 5. And then back to list, ops, sequence. And then we just name our sequence. Now here we can't use x as the counter because x is our real variable. You could use a, yeah. Pretty sure we did this last week too. 4. Just 4 for now, yeah, 0 to 4. So my expression is x raised to the a divided by a factorial. Variable is what here? X or a? A, excellent. Starting at? Excellent. Yeah, we have to be very conscious of starting at 0, 1, or something else. We're going to end here at 4. Step is optional, but you can put 1 in if you want. Paste. And then graph. It's not exciting. 4 terms isn't exciting. Zoom 6. It's not okay. It's thinking. Okay. Should look like that if you did it right. Did you go from 0 on up? And you have, oh, maybe is your window the same? Oh, let's see. Yeah, something's wrong. Y equals some sequence. Oh no, we're not doing e to the x. We're doing the terms. Yeah, so you should have x to the a, x to the a over or n. Yeah, so you had the wrong thing there. Okay, if I compare that to e to the x, I'll see that they match for a little while. Where's e to the x? E to the x. So on my graph, it looks like they line up pretty good from like -2 maybe to +2. I'll zoom in there to see it better. Window, let's go -5 to 5. And y, let's go from 0 to 10 is fine. I just redid it. So here I'm going from -5 to 5, 0 to 10. Really? It says error.
And when I think go to, it's like factorial.
That's subsequence. You're like,
Sum. Oh, is that? That's divided by a factorial. Oh, you're closing something prematurely here. You have an extra parentheses there, and there, and there, and you need another parenthesis there. There you go. Okay. I think, is that looking better? It's thinking. Okay. Yeah. So if we added on more terms, it would be tighter. But again, we have a problem with processing power in more terms. Do you think the calculator could handle 100 terms? No. GeoGebra was freaking out with the Bessel function, which is a lot more complicated than the exponential function. But here we can see we're relatively tight between -1 and 1, and then after that we're diverging. What do I mean by relatively tight? Well, if I hit trace and I go to a number near x equals 1, which is right around there, I can see the sequence says the y value should be 2.88, and the actual function says the y value should be 2.89-ish. So I'm about 100th off at x equals 1. Okay, so in a little while, toward the end of the class, we'll take a look at how do you do error analysis on Taylor polynomials. Well, if you just hit trace and then type 1, you don't even need to go to calc. Yeah, a little quicker. You learned something. Too bad you don't have a calculator with you. I'll go get you one. Yeah. Yeah, so if you're in trace mode and you type a number and hit enter, it'll plug it in and give you the number. You can switch functions by going up and down, type 2 again, hit the number. Yeah. Okay, new problem. What we're going to do is we're going to develop a 4th degree Taylor polynomial for the cosine of x. Okay. So focus, come on. How did we create the 4th degree Taylor polynomial for e to the x? How did we come up with that the other day? We take repeated derivatives, right? So we need to take repeated derivatives of cosine. Okay. Now, what was our center for e to the x? Can anyone tell me? What's the center of this power function or this power series? Yes, say it again, Courtney. Yeah, the center is 0. Yeah, c equals 0. Okay, so we're going to stick with the cosine with center is 0. Okay, so we're going to center it at 0. Okay, now when we took repeated derivatives of e to the x, what popped up in those coefficients? What was the significant thing we discovered? Yeah, there were coefficients. What are the coefficients?
They were always 1 over n factorial.
Yeah, there was always 1 over n factorial. So it turns out with Taylor functions, you're always going to have those factorials in there. Now, e to the x, what's its derivative all the time? It's e to the x, and then we were plugging in 0. E to the 0 is always... So the only thing e to the x contributed to this power series at each stage was that its derivative evaluated at 0 was 1, 1, 1, 1, 1. Okay. The fact that we're trying to find a polynomial is where the factorials came from. Because if you take repeated derivatives of things like x to the 4th, what happens? It runs out of powers, but what accumulates in front of it? Like what if I take repeated, like what if I take the, let's see, the 10th derivative with respect to x of 10 to the x, or x to the 10. Shit, I wrote that backwards. Right? The first derivative is going to be 10x to the 9th. The second derivative is going to be 10 times 9, x to the 8th. So I'm going to have a 10 times 9 times an 8, keep going, and then I'm going to run out of stuff. Right?
Right.
Okay, so what happens when I take derivatives of polynomials? What do the coefficients look like? They look like factorials, correct. Okay. So the trick, the shortcut for Taylor functions, because we did a little more work than we need to in the future on this, the shortcut is the coefficients, the a sub n's, are always going to be the nth derivative of the function evaluated at the center divided by n factorial. These are Taylor, what's that? No, well, the one only happened with e to the x, right? Because the derivative of e to the x is e to the x, and e to the 0 is 1. So because the center was 0, and because we were using e to the x, we always ended up with 1 from that function. My numerator was always 1. The function we choose will give us different numerators, but the denominators are always n factorial. Okay? Because what is a Taylor polynomial? In essence, from last class. What were we trying to do each step of the way last class? Oh boy, that was a long time ago, I know. First we started off finding a tangent line to e to the x, right? Then what did we find? A tangent parabola, tangent cubic, and then we found a tangent quartic, right? Remember, it was like mind-blowing. It was so exciting we might even get that tattooed around our arm, okay? Taylor polynomials are tangent polynomials. So guess what a first degree Taylor polynomial is? It is a tangent line. You are the winner. Yes, you deserve a prize for that. Yeah, it's a tangent line. All Taylor polynomials do is extend the idea of a tangent line to higher degree polynomials. And then we try to take it to infinity and turn them into power series. Does that always work? Most of the time, not all the time. All right, so we are trying to find a tangent polynomial for the cosine of x. We are going to turn the cosine into a polynomial. To do that, we need repeated derivatives. So let's get busy. Okay, first thing we need is what's called the 0th derivative, which is the function itself. So just keep that in mind. There's always a step 0 here. Step 0 is what is the function itself. Well, I'm going to call the center C instead of A, because I'm using A for the coefficients. Sorry. Yeah. So here, in this particular case, I'm going to let C equal 0. Is the center always going to be 0? No, it depends. We got to pay close attention to that. Like, we couldn't do a center 0 for the natural log, because the natural log of 0 is undefined, right? So that'd be a problem. Okay, so, and we're going to take a bunch of derivatives, but this is just an important note. The 0th derivative of a function is the function itself, according to that notation. All right, so I'm going to make a table. I'll do the table in a minute. What's f prime of x? Negative sine of x, correct. What's f double prime of x? Negative cosine. F triple prime. And the 4th derivative? Now, I don't want it at the moment, but I'm going to write it down anyway. If I did need the 5th derivative, what would the 5th derivative be?
Oh my gosh, it went back to the beginning.
Interesting pattern here. So there's something cyclical about a sine. Well, we knew that. Sine's a periodic function. So is cosine. Okay. All right. Now, okay, we got the first derivative. Then once we find it, we plug in our center. What's our center?
0.
So f prime of 0. Sine of 0 is 0. Oh, we forgot our original function up here, yeah? F of 0 is 1. Okay. F prime of 0 is 0. F double prime of 0. What's the cosine of 0? It's now negative 1. F triple prime? negative 0, f fourth prime, and just for fun, if we went for the fifth one, what would it be? 0 as a coefficient, that means it disappears. So this is interesting. For this particular Taylor polynomial, the odd terms vanish, but the even terms remain. Okay. All right, so let's see, go back to the formula for Taylor series. For a Taylor series, or Taylor polynomial, the coefficients, I'm calling them A sub n's this time, is the nth derivative evaluated at the center, in this case 0, over n factorial. So let's write down what we have. So we are going for a fourth degree Taylor polynomial. So I'm going to call it t sub 4 of x. And the 0th term is what? 1. Okay. So I'm going to get a 1 plus the first end of the x to the first term is 0. So I'm going to write it down anyway. So this is a 0 over 1 factorial times x to the first. And I'm writing it down for a reason I'll get to in a second. The next term, coefficient is negative 1 on top, negative 1 over 2 factorial times x squared. What's the next term going to be? 0 over 3 factorial. And I know that's 0, but I'm going to write it down anyway. And then the last term I care about at the moment is what? 1 over 4 factorial? Yeah, don't forget the factorial, times x to the fourth. So I can write this with less ink, true? Yeah, this term is 0, this term is 0. One reason I wrote them out is I occasionally will do something like this. So the first term is 1, there's no next term, and so I'll get its coefficient, which in this case is what, negative 1/2, and then I'll just put an x by mistake, when I really should put an x squared. So just be super careful. If terms do 0 out, make sure you keep track of the right powers. All right, plus there's no third term, but there is a fourth term, 1 over 4 factorial, which is what, 1/24th? X to the fourth. Now, does anybody want to take a guess at what the next term might be? Now, this is what I want. This is all I really wanted to find. I got my Taylor polynomial, fourth degree, done. Okay, so there's no what? There's no fifth term, but there'll be a sixth term. What should the sixth term be? 1 over 720, which is 6 factorial. Is it going to be positive or negative? Yeah, positive, negative, positive, negative. It's probably going to be negative, and then the power is x to the 6th. Okay, so if I continue this, the combination of all these guys would be called what? Taylor polynomial of what degree? 6th degree. Yeah, this would be the 6th degree Taylor polynomial. 6th degree. Okay, I would like you to graph that, the fourth one, and compare it to the cosine of x. I'll be right back.
Yes, I gave them the test. They're right here. Can
Okay,
you...
I'll check on you guys in a little while. I'm just in the other room if you have any questions. Thanks, Catherine. All right, Jeff, you're killing me. Stop gabbing. Get to work. Graph it.
There's a lot of scatter plot on here.
Oh, yeah, that was an interesting problem. I'll explain that later. No, I can reproduce it easy. Yeah. You got to change the mode, though, to get rid of it.
You're gonna have to ask. How would you graph this? Enter it in.
This one, I would just enter it exactly as I've written on the board. Don't worry about some sequence right now. Because have we written this in a sigma notation?
I would just write like.
You would write 1 plus -1/2 times x squared plus 1/24 times x to the 4th. Yeah.
First, trying to get the cosine of that.
Yeah. We want to see how it compares.
Oh my gosh, it's so weird. Beautiful.
Oops.
That's really cool. Do you want us to compare it to cosine?
We're only doing the 4th degree first.
Just the 4th degree first, yeah.
That's pretty cool. That's cool.
I messed up my range. What did I do wrong?
I like that we're using algebra.
Are we?
Oops, there's the problem.
I feel like a little bit. Maybe not a lot.
Let me see what you put in.
I like algebra.
Okay, so there's my 4th degree polynomial, right? That should be what T4 looks like for cosine. At this point, it doesn't matter. But to do cosine, calculus and trig functions have to use radians. Otherwise, everything goes to hell. Okay? Has to. So I better check my mode. I'm in radians. Yeah, the 6th degree is going to look different. You're going to get more wiggle. I wanted to graph the 4th degree first. Cosine of x. I'll do the 6th degree by just adding a term on next. Okay, and so, yeah, so we got to do a couple of things. We got to figure, okay, that's not bad. The first hump of the cosine looks like this. If I add that extra term, hopefully the approximation will spread out to be better. So I'm going to add that extra term to mine, which we believe, we didn't really calculate it, but we're guessing based on the pattern, that it is minus x raised to the 6th over 6 factorial, which we believe to be 720. I'm pretty sure that's right. Graph. Okay, here comes the 6th degree Taylor polynomial, and it should hug the cosine a little longer than the 4th degree did. Okay, is there going to be a 7th term for this? Well, yeah, but it's 0. Okay, 8th term. Can we guess what the 8th term is? Let's put it on there. So I'm going to go to the end here. Let's see, is it going to be positive or negative? Positive.
Positive 1 over 8 factorial times x to the 8th.
Correct. Yep. So plus. So I'm going to write it as x raised to the 8th over 8 factorial. Another way to list that. Over 8 factorial. I'm just going to go to the math menu and steal the factorial button. Okay. I'm going to graph that sucker. So this should hug it. So if I narrowed my window, it would be hard to tell the difference in between certain x values. And those x values appear to be like 1, 2, 3, 4-ish maybe. So if I were to just change my window and turn off the cosine, so I'm just going to do that for fun. What if I went from -4 to 4? And I showed this to my trig class. What might they think this is the graph of? That looks a hell of a lot like the cosine, doesn't it? Yes, that's true. But that looks a hell of a lot like the cosine, doesn't it?
Yeah.
Right? Now, I'm not showing the cosine there, so you can't see them deviate, but at the edge of that window, they do deviate. We are deviant sometimes, aren't we? Yeah, so here I can see the deviation at the end. So there is some error that's noticeable toward -4 and toward x equals 4. Okay, let's see if we can come up with a series formula. Like, what was the sigma notation look like for this? See if you can guess at that.
Oh, well, okay.
Give it a shot. So I'm going to summarize my work in a table. Oh, shit. I hate when that happens. I just did. Give me a few minutes. Yeah. Whoa, my pen freaked out a little. It's supposed to be sign. Oh boy, it's getting worse. 0, 0. -1 over 6 factorial. All right, so we started to see the pattern, right? So what's the cool thing about the pattern here? It's these first 4 terms repeat in the derivatives. So that means as far as the coefficients, I'm going to have a repetition of the numerator part. So I know it's going to go 1, 0, -1, 0, 1, 0, -1, 0. And the denominator changes after that. So then the question is, can we somehow generalize this for n? Right? I can tell you, like, if you tell me n is 104, I can tell you which of these guys we're looking at. Okay. That means I know whether it's a 1, 0, or -1. And I know what 104 factorial is. It's big, but you know, I can nail that coefficient. So the big problem here, I think, is nailing what is the -1 to the power. And then how do I designate an even number as opposed to an odd number with algebra? 2 times something. Now here, if I could do this. I could just call it n factorial, and as far as the question mark goes, I could just make a comment. N is even. Now that alternation here is a little bit of a trouble. Every other even term is negative. I can put it in words. I just did. Every other term is negative, right? Okay. Yeah, I do. So instead, I'm going to change to a different letter instead of N. I'm going to use M. So I'm going to go to a new page. Okay. Yeah. So I'm going to say 2M equals N. Because this way, if M is an integer, it guarantees me an even N. You agreed? If N is like a counting number, a whole number, if M, there we go, is a whole number, then N is now even. Okay. So does M have to start at 1 or 0 here? 0. It's got to start at 0, right? And notice I originally said integer, then I changed my mind, I said counting number, then I changed my mind again and said no, whole number, because I have to get a 0 out of that, because I'm trying to generate the series 0, 2, 4, 6 for n. Okay, so now I have -1 to some power over 2m for my coefficient. Is it sufficient to just put an m up there, or should it be an m plus 1? Let's see. If you check it for 0, so if m equals 0, then that's going to give me -1 to the 0 over 0 factorial, which equals 1. If m equals 1, then that's going to give me -1 to the 1 over 1 factorial, or no, 2 factorial, sorry, which is -1/2. Is that leading the right coefficient I have? Okay, so what you do is you guess as to whether it's an m or an m plus 1, and then you check, see if you did it right. You with me, Courtney? I'm trying to pick values for m to get this list right here. So this right here is where m is 0, here m is 1, here m is 2, here m is 3. So I'm trying to find a way to skip over the odd terms. So to do that, I had to introduce a new letter I was calling, oops, wrong way, m. Yeah, oh, sorry, this should be a factorial.
Okay.
Sorry.
Yeah, that's what I got.
Should be a factorial like that. Okay, so I think I have a series now for cosine. I think it looks like this. I think the cosine of x is equal to the infinite series as m goes from 0 to infinity of -1 to the m over 2m factorial times x to what power? The m or the 2m? 2m is correct. Pretty cool, huh? So now, let's see, wait, is cosine an even or an odd function? Anybody remember?
It's odd.
It's pretty odd.
Even means symmetric about the x-axis. Odd means symmetric about the origin. Do either of these graphs appear to be symmetric about the x-axis? Yes, so cosine is an even function. That's one way to get to it. Sine, guess what the sine is? Sine is odd. Darn, sine is odd. It's symmetric about the origin. What kinds of powers did we end up with the cosine's Taylor series? We have only what kinds of powers? Even powers, because it's an even function. The sine, it will have all the odd powers. Yes, they are complementary functions in that way. Okay, so I need to shut up here because we got to do a survey. So you guys need to meet the surveyor. No, you cannot leave. You need to meet the surveyor first. I'm going to